This video is part of the MCAT chemistry video course. Subscribe and hit the bell if you'd like notifications about the release of new videos, and please visit ancientbrainstutoring.com for questions about one-on-one virtual MCAT tutoring. In this video, we're going to start going over kinetics, and we'll start by talking about the activation energy and kinetic versus thermodynamic control. The activation energy has been covered in the video on free energy and enthalpy, and we said in those that it's the minimum energy required to start a reaction. And if you look on the left at this image here, we can use it to get a little bit better intuitive understanding of this. So remember that molecules are always bouncing around. And whenever a reaction happens, those molecules need to hit each other, and there needs to be two things that happen in order for the reaction to proceed. One, the reactants need to be oriented in space in the correct way. And then two, they need to hit each other with enough energy to overcome that activation energy barrier. That helps to understand this idea that increasing the temperature increases the rate of reaction because it increases the number of collisions where the molecules have enough energy to overcome the activation energy barrier. And then the other thing it helps to explain is that how catalysts lower the activation energy. And the way that catalysts usually do this is that they orient, so they change the orientation of the molecules in space, and they do it in a way that helps this reaction to occur with less energy requirement. And sometimes it's not just through orienting the molecules, but it may actually change some different things about the local environment, like maybe some pH changes, or maybe it puts some charges nearby the molecules that somehow affect the reaction. Regardless of how they do it, a catalyst lowers the activation energy. The effect of a catalyst is summarized in the graph on the right. And one thing that we really want to make note of is that the reactants are starting on the same spot for the free energy graph, and the products are ending on the same spot. So the catalyst did not change the free energy. So that means it did not change the change in enthalpy, the change in delta G, or the change in entropy. All it changed was the activation energy requirement. All of this is summarized in the Arrhenius equation, which we have K, which is the rate constant, and then that equals this equation. And the rate constant will be covered in the next video. But basically what K is you're going to multiply that by the rest of the rate law, which is covered in the next video. And as K goes up, the rate goes up. And as K goes down, the rate goes down. And so that's what you want to focus on, is the change in K and how that relates to the change in the rate. So we take that equation and we rearrange it how we have it on the right. And all we did was we used our rule for a negative exponent. So if you ever have something raised to the negative exponent, you can take the reciprocal of that number and then raise it to the positive of that same exponent. So notice how our exponent, negative EA over RT, is the same, but now it's the positive version of it because we have 1 over that value. What this allows you to see a little bit more easily is that if we change EA, so EA is the activation energy, and if EA goes up, then the bottom part of that fraction is also going to go up. And if the bottom part of that fraction goes up, then K will go down for that situation. And then reverse your thinking for the temperature. If the temperature increases, then the bottom part of that fraction is going to go down, which means that K is going to increase. So give yourself a second to think about how those numbers would change that fraction and then how that would change K. I wouldn't really worry about memorizing this equation, and in all honesty, the only thing you really need to take away from it is that when activation energy goes up, the rate goes down. When temperature goes up, the rate goes up. Some reactions are going to be able to create different products based on the different conditions that the reaction is taking place in. If you look at this graph, we can see that one reaction is represented by the red line and one is represented by the blue line. Notice that the red line has a higher activation energy and the products have a lower free energy value, versus the blue line has a lower activation energy and the products have a higher free energy value. This would mean that the products on the red line require a higher energy in order to start that reaction because they have a higher activation energy. So those are called the thermodynamic product because the products have a lower free energy value, which means that they're more stable. And we call that the thermodynamic product, or we say that that reaction is under thermodynamic control. For the blue line, those products are less stable, but the blue line has a lower activation energy, but they are less stable products. And we would call those the kinetic products, or we would say that they're under kinetic control. Think about what conditions we would need in order to form each one of these products. So for the red line, we would need a high enough temperature in order to overcome that activation energy. So to form the red products or the thermodynamic products, we need a high temperature. And then conversely, if we have a lower temperature, we won't have enough energy to reach the activation energy for the red products or the thermodynamic products. So the kinetic products get formed under cold temperatures.